Today, we will be deriving internal shear and bending moment equations for a more complicated loading system. This video is a continuation of my first video on deriving internal shear and bending moments, which you can find in the mechanics tutorials playlist on my YouTube channel. So, just like last time when we had a simply supported beam, the first step is solving the reactions at the two supports. In this case, we have a roller on the left side, meaning we will have a force in the y direction and a force in the x direction. And on the right side of our beam, we have a roller, which is indicated by these three circles that kind of look like wheels at the bottom. And for a roller, we're going to have one reaction force right here. And so, as usual, we'll take our equations of equilibrium. So we'll start with some of the forces in x. And before we move on, I'll just label these reaction forces. So let's call this side of the beam A, and let's call this side of the beam B, giving us Fby, the force at B in the y direction, force Ay, and force Ax. So to start off, we know some of the forces in x is equal to 0. And so what that tells us is Fax is equal to 0. Which makes sense because we do not have any loads acting in the horizontal direction. So this support does not need to resist any loads in the horizontal direction. Let's now move on to some of the moments around A. So we take some of the moments around A. We know that those are equal to 0. And when we take moments about A, we know that forces acting directly into that point do not create a moment because they don't have a moment on them. And what this will do is it'll allow us to create an equation that isolates Fby, and then we can solve for it. So we know some of the moments around A is 0, and I have my positive sign convention here, showing that counterclockwise moments are going to be positive. So we know that 0 is equal to, so the moment caused by this uniformly distributed load is going to be 4 kilonewtons per meter acting over a distance of 4 meters. And we know that the equivalent point load of a UDL is going to act directly in the center of it, which is going to be at a distance of 4 meters divided by 2. 4 meters. Actually, I'll stay on this side. I'll make this look a little bit neater. We know that it's acting at a distance of 4 meters divided by 2 from point A, because we would have 4 meters, cut that in half, and that's our moment arm. And that is going to be going in a clockwise direction, which is negative, according to our sign convention. Next, the moment caused by the 2 kilonewton point load. We see that that is going in the counterclockwise direction around point A. So we will add 2 kilonewtons acting at a distance of 4 plus 1 meter, that's 5 meters total. And then finally, we have the moment caused by Fby, which is also going to create a moment going in the counterclockwise direction. So we have plus Fby acting at a distance of 4 meters plus 1, that's 6. So let's simplify this. 0 is equal to negative 4 times 4, that's 16, times 4 divided by 2, which is 2. So then we get negative 16 times 2 is negative 32. Plus 2 kilonewtons times 5 meters gives us plus 10 kilonewton meters plus FBY times 6 meters. So let's move these numbers over to the other side. So we'll get 32. I'm going to leave the units out for now just to speed up the writing process, but everything's going to be in kilonewton meters from this point. So we add 32 to both sides. We get nothing on this side, positive 32. Subtract 10 from both sides. We'll get a negative 10 on this side. Equals FBY times 6 meters. Divide both sides by 6 meters. These will cancel out. Divide by 6 meters. And then we get FBY equals 32 take away 10 gives us 22. Divide by 6 equals 3.67 kilonewtons. Okay. And then to finish this off, we'll do sum of the forces in Y. And that will be our third equation of equilibrium, which will allow us to solve for FAY. And so when we take sum of the force of Y equals 0, we get 0 equals FAY, take away, because this UDL is going downward, take away 4 kilonewtons per meter times 4 meters, because that will give us in units of kilonewtons, plus 2 kilonewtons, plus FBY, which we know from some of the moments is 3.67. Okay, and let's simplify this. 0 equals FAY. Negative 4 times 4 is negative 16. Negative 16 plus 2 plus 3.67. Move everything to the other side, and we get FAY equals positive 16, take away 2, take away 3.67, because we're canceling out everything over here and moving it to the other side. And we get FAY equals 10.33 kilonewtons. And then let's write that on our diagram, just so we remember it. So we have FBY, 3.67 kilonewtons. FAY is 10.33 kilonewtons. Okay, so everything from this point has been the exact same as our simple beam loading condition, but now this is where things get a little bit different. So in the first video, we saw a simply supported beam which had 2 supports, and it had 1 uniformly distributed load going across the whole beam. And that was convenient because the loading pattern doesn't change at all, which means that when we develop an equation, that equation was able to hold true for that entire beam, because we know from the last video that the internal shear and internal bending moments are directly dependent on the loads, because we needed to use the loads to find those equations. So in a situation like this, where we have a UDL until here, and then all of a sudden the UDL stops. It goes away in this meter right here. and then we have 2 kilonewtons here, and then another meter. We can see that the loading conditions are changing throughout the beam. So we can see we have in this section here, we have a UDL, and then boom, loading condition changes. So this is a different loading condition because the UDL goes away. And then the point load changes the loading conditions again. And so that area has different loading conditions. And so the reason why I'm drawing these out, these are going to be important for later, but what I want you to remember from this part is because the internal shear and bending moments are dependent on the loading conditions, when the loading conditions change throughout the beam, the equation actually changes because we know the loading pattern is changing, right? So in a UDL, the load is constant and we can make an equation that works for this entire distance. But that equation doesn't work anymore when we hit this section because the UDL is gone and the loading conditions change. And so we end up with these different, almost like pieces, these different loads that are creating different sections of the beam that will have different equations. And I hope that makes sense. If there's any confusion, I think it'll help to keep moving to the other examples. And of course, if you're still confused, feel free to drop a comment and I can try to explain it further. But to summarize that, what I want you to remember is this. When loading conditions change along a beam, we need additional, I should be plural. When loading conditions change along a beam, we need additional equations because the internal shear and bending moment equations depend on the loads that are being applied. So when the pattern breaks, our equation breaks and we need a new one. So these 3 cuts I made here, the first cut is in the UDL, and then when the loading conditions change, I made a second cut. Loading conditions change, made a third cut. So whenever you see a new load appearing or disappearing, that means the loading conditions are changing. And so these 3 cuts capture the 3 distinct locations in the beam with different loading conditions. So I'm going to call this cut 1, cut 2, and cut 3. And I'll label these over here. I'm going to run out of room, so I'll quickly scooch some of these over. So this one will be cut 1, cut 2, and then cut 3 will be over here. And just like something like this. And so essentially, what I've done is, just like in the example we saw from the last video, at each cut I've made, I've only taken the left section of that beam from the cut and moved it over here. So at cut 3, for example, I keep the UDL, I keep this section, I keep the point load, and I cut it here, and I've simply dragged it over here. And just like last time, that leaves us with internal shear and internal bending reactions at each of these points. And you'll remember from last video that we're not adding any new forces here. All we're doing is we're replacing one side of the beam with the equivalent shear and bending that it's causing. And this allows us to evaluate the shear and bending at those individual points. So now it becomes like the old problem, except now we're going to have to do 3 distinct calculations to find our equation. So let's start with number 1. We know we have 4 kilonewtons per meter, and this distance, remember, we want a general equation for any point along that section where our equation is going to apply. So we're going to call this distance here x, because we want a variable. We want to write these forces in terms of our variable x to get that equation in terms of a position on our beam. So we know force right here is just like it is right here, 10.33 kilonewtons. And then we have V and we have N. So to find V, just like last time, we'll have sum of the forces in Y equals 0. 0 equals 10.33 take away 4 times x, because 4 is our UDL acting over a distance x, and we add V to that. And I'm going to leave units out of this one, just to simplify it, but this is in kilonewtons and this is kilonewtons per meter. So then we rearrange for V, and we get V equals 4x take away 10.33. And then for the moment, we can take some of the moments around point A. So remember, this is point A. Some of the moments around A are equal to 0. So what we have here is 0. I'll grab my chair again because I'm getting too low. 0 is equal to, so we have the moment from this UDL going in this direction, which is the opposite of our sign convention. So we'll have negative 4 acting at a distance of x, or sorry, acting over a distance of x to get our equivalent point load. And that point load acts at the center of this UDL, which is half of x. So x over 2. And then we have a counterclockwise moment caused by our shear acting at a distance of x. And then we have our moment acting counterclockwise according to the sign convention we use here. So remember that you can guess this to be up or down, you can guess this to be clockwise or counterclockwise, but it will change your sign depending on which one you pick. But stay consistent to this and everything will work out okay. So then, solving for m, we get m equals, so this right here is 4 divided by 2, that's 2, times x, we get 2x squared. And so I'm moving this to the other side and just isolating for m. 2x squared minus v times x, and v is 4x take away 10.33 times x. And then simplifying this, 2x squared take away 4x squared plus 10.33x. And then finally we get moment is equal to negative 2x squared plus 10.33x. Okay, and now we have our shear and moment equations in terms of x, but if you remember our rule, loading conditions change along the beam, when loading conditions change along the beam, we need additional equations. These equations are only valid in the region of our first cut in this section where loading conditions are constant. So this is valid over this space right here, or we can write it a little more formally. Let's say x equals 0 is at our left support. So then this equation is valid for 0 must be less than or equal to x, which must be less than 4. And so the reason why I'm saying less than 4 is because 4 is kind of our boundary. Well, I guess this could be less than or equals to. But as soon as we step outside of 0 or outside of 4, the loading conditions haven't changed, and so the equation for shear and moment, those relationships are going to be changing in a different way than they were during that first 4 meters. And so same thing down here. 0 must be less than or equal to x, which must be less than or equal to 4. And so this is the full process for getting your shear and moment equations for any complicated loading system. So as long as you break it up, so add new cuts every time the loading conditions change, that will give you the 3 different sections that you want to take, and then you solve for this shear and moment using the loads and the forces you calculated at the start. Or should I say, the reaction forces you calculated at the start. So, for these 2 examples, you would repeat the exact same thing, where you have that shear and moment, except now, when you take some of the forces in Y and some of the moments are on A, you're going to get some different values, because here you have slightly different loading conditions. V is at a longer length. Over here you have a point load, so they're going to change. So what I want you guys to do is work on these other sections in your own time, and I'll provide some sort of answers included with this video so you can check. But before I let you do that on your own, I'll get us started on this one right here. One thing I want to mention before you guys try this on your own is to label X across the whole area. And the reason you want to do this is because you always want to be measuring X from that same reference point. That point where we said X is going to be equal to 0. Because when we list these restrictions right here, when we say X must be between 0 and 4, that tells us X, what's measured from here, can be anywhere from 0 to 4 meters away from it. And so when we make the domains for the other one, we want our domains to be, for section 2, for example, we want our X domain to be between 4 and 5, and then for cut 3, between 5 and 6. but it's important that we measure x from that same location every time, which means that we need to make x this full distance, because this is our reference point, where x equals 0, and then we measure it all the way to the other side. But when you take, so then this makes it a little more tricky. So for example, when we do, let's do sum of the forces in y. So we have this x distance here to work with. We also know that this is 4 meters across right here. Because we have this 4 meter section, and then x is going past that. So we're looking at this section right here past 4 meters. So we know that this UDL is 4 meters long because we get to the end of it, and then we go a little bit past this. And so this x direction takes care of that extra little distance. And I'll walk us through the sum of the forces in y, just so you can see why this might make things a little confusing, but it's not too bad once you get the hang of it. So we know sum of the forces in y equals 0. So then 0 is equal to, so we still have our 10.33 kilonewton reaction. So 0 is equal to 10.33. And then subtract 4 times 4 meters. Or not times x anymore, because we know the full UDL is getting used here, because we're in the section that's now past where that UDL ends. So take away 4 times 4 plus v. And so you'll notice that when we solve for v, we will get 10.33 take away 16, that gives us negative 5.66, move it to the other side. V is equal to 5.66 kilonewtons. And so you may be wondering, oh, why do we not have an x in here? But this makes sense because in this entire section, the shear is constant, because in this section, just looking at this part right here, there's no loads in there. And we know that shear and bending moment are dependent on the loads acting in that point. If there's no loads in there, then the shear and moment simply don't change and will remain the same. So sometimes you will get answers where the shear is just a constant. It doesn't depend on x. And this happens in sections of the beam where there are no loads acting. So to summarize everything in 3 simple steps for you guys, I want you to remember that the first step is solve for support reactions. And this is something you will always need to do when you're solving for internal shear and bending, because those values are needed to determine the value of this shear and moment when you cut your sections. And then the second step for any loading condition is cut beam in all places where loading changes. So just like we did over here. So we start from the left side. Well, UDL is added onto our structure, so we cut in here. The UDL goes away, which means the loading conditions change, and we have another cut. And then this point load changes the loading conditions again for our third and final cut. And then the final step is solve for V, shear, and M, moment, at all cuts in terms of x. And remember that for x, we are always going to make x the full distance from the support to wherever our cut is. And that's pretty much it. So for extra practice, finish this problem here, or this cut here and this cut here to get your last two equations. And I will include those answers in the description so you guys can know if you got the right answer. And as always, thank you for watching, and comment if you have any questions or anything that I can clarify. Thank you.